Hi guys and welcome back. So here we have a Dell laptop for repair from a customer. So this laptop doesn't turn on, so it's a no power case. So let's try to fix this laptop today. Okay, let me connect the adapter. So look at the ampere reading. Yes, so it's drawing around 51 milliamps. Okay, so this is little bit higher than usual, so that should be somewhere around 30 to 25 milliamps. So 51 is fine, so it's not too much. Okay, so let me connect and try to turn on the laptop. So if I press the power button, yeah, so we don't have any response, no changes on the ampere reading. Okay, so we can open the laptop and check first whether we have a main power rail on this motherboard here, which is 19 volt. Okay, so we can check the main power rail on this capacitor here, so you can see, which is 25 volt filter capacitor. Yes, so 25 volt filter capacitor, and this should be connected to the main power rail. Okay, and yeah, checking the voltage. Yes, so we have 92.6 volts, so the main power rail is present, so there's no problem. And if you check the inductors, we have 0.6, okay, 1.8 volt, so another 1.8 volt. So these two are primary voltages for the PCH inside this SoC here. Okay, then we have 3.4 volts, so this is the standby voltage. Okay, 3.4 volt, that is for mostly for the deep sleep well of the PCH. And at this point we don't have anything. Yeah, 5 volt, I think. Yes, 5 volt is present, and that's it. So almost all the base voltages are present on this motherboard here. Okay, right. So the question is, why does the board is not turning on if you press the power button? Okay, right. So first we can open the motherboard and just have a visual inspection, and then we can start our diagnosis based on the power sequence in this motherboard here. Okay, right. Before that, we can just have a diode value of all the inductors. Right, so first we can check from the main power rail back to all inductors. 445, okay. 445, yes, 400. 400, fine. Yes. Good. Okay. 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 Yeah, that looks fine. So all the upper MOSFET are okay. Let's check with regard to ground. Battery coil, so this is not the battery coil, something else. Okay, maybe the RAM coil. So if we disconnect the RAM, we can find more impedance. Yes, so 132. Once we connect the RAM, we will get a low reading. Yes, so this is the RAM coil. Yes, so that is fine. This is 3.3 volt. Okay, the CPU core voltages. Yes. Another 0.3 reading. Okay. Yes, 0.064. Primary voltages. Yes. So all the inductors are okay. There's no short directly on the inductors. So I will take out the motherboard so that we can start our basic checkup using the power sequence in this motherboard here. Okay, right. Okay, so the board is out, so everything looks fine. So there's no any burn marks or visual corrosions on this motherboard here. Everything looks fine. Let's check once again. So here we have the first and second MOSFETs. Okay. Yeah. Okay. We have the charger IC, which is intersil charger IC 95522H. Okay. That looks fine. All right. So everything looks fine. So let me connect the adapter. Yes, 50. Wow, the board is turning on. Okay. So it is drawing around 1 amp. Right. So what did happen on this motherboard here then? So once we remove the main battery on this motherboard, so the CMOS reset event has happened here. Okay. Right. So we have the RTC battery inside the main battery here on this motherboard because we don't have RTC's battery socket on this motherboard here, the coin cell. So that is inside the main battery. So once we remove the battery, the CMOS reset event has happened on this motherboard. So that's why now the board is turning on automatically. So we didn't press the power button. The board is automatically turning on once we connect the adapter. Yes, so it's turning on and it is working fine. So 900 milliamps is perfect for this motherboard to execute the display. And let's check if we disconnect the RAM. What's the reading? Yes, so that is around 950 milliamps, so that is fine. And if we connect the RAM, we will get around, yes, so 1 amp, 1.04 amps. Okay. Right, so I think everything is working fine. So just a simple fix. So I should have done this before without removing the motherboard from the laptop. Yeah. Okay, so we will follow this procedure in our future repairs. So if you don't have the CMOS battery on this motherboard here, then it will be inside the main battery. So just removing the main battery will have the reset to the CMOS as well, because the CMOS battery is inside the main battery. Okay. Right, so that is fine. So let me just assemble this inside the laptop to see whether we are getting a display. Okay. Okay, I have just assembled the motherboard inside this laptop. So I have connected all the connectors. So let's go for a last test to check whether everything is working. Okay, connecting the adapter. Yes, you can see it is drawing around 1 amp, 1.1 amp. Let's wait for the display. Yes. $65, 650 amps, shutting down, turning on again. Yes, 1 amp. So most probably it is power cycling, no problem. Come on, give display. So we have a light blink on this side. So that is 1, 2, 3, and 1. So most probably this is the CMOS reset warning. So once we press the power button and shut it down, it will be reset. Yes, so turning on. Now I have pressed the power button. It is turning on. Okay. We should get a display this time. Yes, we got the display. And I think everything is working fine. Yes, so time is not set. And yeah, alert power AC power adapter wattage and type cannot be determined. So this adapter does not have the PSID capability. So it had before, but it became malfunction. So it was not working for more than like 3 months before. Okay. Anyhow, if I connect the Dell original charger, it should be charging. So that's the error on this point here. Okay, we can just click continue. Let's see whether it is booting into Windows. Yes, so you can see the Windows is loading. Okay, just look at the ampere reading now on the DC power supply to see the ampere reading when it is on the standby, right? Yes. So now you can see the ampere reading is going to 50 milliamps, then coming back to 20 milliamps. So this is the usual ampere reading in this laptop here. So let me connect it again. Yes. So going to 41 milliamps, then back to 24 milliamps. So now we can check what are the voltages present in this motherboard at the standby before pressing the power button. Okay, right. Yes, okay, checking the voltage. 3 volt present, 5 volt present, 1.8 volt. This is not present. Okay, we have this 1.8 volt is present. So earlier we had two 1.8 volt before resetting the CMOS. Now we are having only 1.8 volt, only one coil here. Okay, yes. So if I disconnect the adapter and connect it again with a multimeter on this point, and we can see whether we are getting a voltage. And you can see the 1.8 volt is coming for a second and it is going off. So it is turning on for a second and it is going off. Okay, and once we press the power button, this 1.8 volt will be present. So earlier we had 50 milliamps. It's because these two 1.8 volts were generated. So that's why we got two of these 1.8 volt before pressing the power button. But now it is going back to 40 milliamps when 1.8 volt is present, and some control is turning off this 1.8 volt and it is going back to 20 milliamps. So that's it. So let's diagnose this through the schematic. So what is actually happening here, then we can understand the power sequence in this laptop here. And also I'll give you an explanation about what is actually a CMOS reset in this motherboard or any motherboard, and what actually happens when you reset the CMOS. Okay, right, so let's get in. Alright, so this is the schematics of this motherboard. So you can see the part number LA-K034P, and this schematics is actually same with LA-K034P. So we attempted a repair of this laptop previously, and actually it was no repair because the EC chip on that motherboard got shorted. And some of you guys gave your comments that you did not understand the power sequence explanation in my previous video, which is the diagnosis of this motherboard. So I'm going to take this as an opportunity to explain you again the power sequence in this schematics, so in this motherboard. So then you will get a good understanding of the power sequence. And here also they are using the same MEC EC chip, which is MEC1515. In this motherboard also they are using the same MEC1515 EC chip. Okay, so I will start from the basic to the end of the power sequence in this schematics here. Okay, so in this motherboard they are using the TGL processor, which is known as the 11th gen Tiger Lake processor, and it is a U processor. So what do you mean by U processor? So there are different kinds of processors. So here we have one. So you have one single die chip inside one single package, and it contains the PCH and the CPU as well. So in one single die chip you have both the PCH and CPU. So most of the Celeron processors, then the Intel Pentium processors, and also the Atom processor uses this kind of CPU architecture, and these are known as ultra low power processors. And the other kind of processor, here we have a dedicated die chip for both PCH. The small one is PCH and this bigger one is for the CPU. And these are another type of processors. And the other processors, you have only one single die, and that is only for the CPU. So this is known as H processor or high performance processor, and it requires a dedicated PCH on that motherboard to function. So most of the gaming laptops use this kind of architecture because it requires high performance. So this type of processor architecture, which has only one die chip that has only the CPU compartment, is known as the high performance processor. And if it has the CPU and the PCH inside one single die chip, that is known as the low performance, so ultra low performance processor. And this processor is known as the standard performance. So what do you mean by U processor here? So if you have both PCH and CPU in one single package, then that is known as the U processor. And if you have only one single package for the CPU, then it is known as the H processor. So here they are using the second type, this one here, because it has dedicated die chip for PCH and the CPU. So then it is known as the U processor, and it uses the standard performance CPU. Okay, right. So when you take about this kind of processor here, the high performance processor, they use the FDI and also the DMI communication interface between the CPU and PCH to communicate between them. And inside this processor, they use OPI interface, or else the OPI connection, which is known as the on-package interconnect between the PCH and the CPU. So they use the copper wires to communicate between them. Alright, okay. So what do you mean by UMA? So UMA means Unified Memory Architecture. So which is known as the iGPU of the CPU here. So inside the TGL CPU, it has a dedicated graphics compartment that is known as the iGPU or Unified Memory Architecture that provides the graphics for the laptop. So this CPU can also provide the DGPU graphics as well through the PCI Express lines. So it provides the video signals through the PCI Express lines, and they can be connected to the dedicated graphics on this motherboard. But currently they are using only the UMA graphics for this motherboard here. Okay, so this is the type of different CPU architectures in this motherboard here. Okay, so here we have the power sequence, the full power sequence of this motherboard here. So power up sequence from G3 to S0. So what do you mean by G3 here? So G3 we call it as mechanically off state. So mechanically off states. So during the G3 state, you won't have the power from the both power source, which is from the battery, from the system battery, and also from the adapter. So when you don't have these two power sources from the motherboard, then we call it as G3 state. You will have only the voltage from the RTC battery here, the coin cell battery. So that voltage will be always present at G3 state. So this power sequence starts from G3 to S0 here. So now let's start plugging the adapter. So once we plug in the adapter, the charger will produce the B plus voltage by driving the first and second MOSFET, and you will have 19 volt approximately at this point here. After that, the 19 volt will go into the standby IC, and then it will provide the LDO voltages, and it will go straight to the double diode in this motherboard. So after the double diode, you will get 3.3 volt as RTC cell voltage. So this is not the RTC voltage actually from the battery. So this is just the RTC VCC voltage from the double diode itself. So let me show you that just for confirmation. So if you copy the signal, you will find it. Yes, going to double diode. Yeah, so here we have the double diode. This is from the standby IC 3 volt LDO voltage, and here we have the RTC VCC. Actually, this is from the battery. This is the RTC cell battery. Okay, let me show you that. Yes, so from the I/O connector on this motherboard, there you have an RTC battery on the I/O board, and the voltage will come from the pin 11 as RTC VCC, and it will be connected to this point here, and after 1 kilo ohm resistor it will go to this anode here, and both of these double diode will produce this voltage. So if the system battery or the adapter is plugged in, you will find this voltage, 3.3 volt LDO voltage on the output side. At the G3 state you will find okay, so at the G3 state you will find only this voltage at this point here. When G3 is not there, or else when the adapter is plugged in or the battery is there, then you will find this voltage at this point here. Okay, so RTC cell is actually the RTC VCC voltage, either from this one or this one here. Okay, so once we get the RTC cell voltage, then this will go straightly into the RTC section of the PCH to provide power for this section here. Then the PCH will receive an input signal as RTC reset and SRTC reset to activate the RTC section inside the PCH. So these two signals are very important if the board is at no power. Then the EC chip will receive an input signal as AC AB in. So this signal comes from the charger IC. So once the charger IC detects that the connected adapter is valid, then it will send the AC OK signal to the EC chip as renamed by AC AB in. Then the EC chip, with regard to this signal, will send an output signal from the EC chip to the standby regulator to provide the 3 volt and 5 volt enable voltage. So then the voltage regulator will provide 3 volt and 5 volt always voltages. So this is VR output, voltage regulator output as 3 volt and voltage regulator output as 5 volt. Then again the voltage regulator will output a signal called POK, means power OK signal, and this will straightly go to turn on the VCC DSW enable signal, and this will switch on the DSW power for the PCH such as 3.3 volt or 1.8 volt. So in this case I think it is a 3.3 volt because you can see 3.3 volt DSW voltage is going as an input to the PCH. So this signal will go straightly to turn on the DSW voltage in this motherboard here. So we can just cross check it. So we can copy this signal. Okay. Yes, okay, so you can see it is going straightly, the 3 volt always is going straightly to this IC here, and this IC will generate the 3.3 volt always voltage for the PCH. So let me check that once again. DSW enable voltage. Okay, we will come to this point later. Yes, so here we have the enable signal. So 3 volt always to 3 volt always PCH. So on signal comes straightly from this signal here, which is DSW enable GPIO, and it will come to UZ4, which we saw before. So it will generate, or it will switch the 3 volt always as 3 volt always PCH. Okay, right. So let me check where does this signal comes from. Yes, so power OK signals comes to this point. You can see here we have SLP SAS signal. So this is commonly used to turn on the primary voltage for the CPU. So it is going to turn on the CPU primary voltage, so that is fine. So this is I think 1.8 volt or 3.3 volt. So let me copy this VCC DSW signal. Yeah, so it comes from the MEC EC chip. Okay, right. So MEC EC chip only turns on the DSW voltage. So this signal goes to this point. So this signal goes to this point, and it renamed after this resistor, as this one here, and it goes straightly to this regulator. So this switching IC will switch 3 volt always as 3 volt always PCH. So this is an output signal from the EC chip. Okay, right. So we got that. So initially this signal is sent from the EC chip. Let me check that here. But they have not mentioned anything on this place here. So this signal is actually given by the EC chip, and this will turn on the always DSW voltage. And this is the primary voltage. So let me copy this signal. So I think both are same. So this is for DSW and this is for the primary voltage. So let me see that. So it is not going to anywhere. Okay. Yeah, it's going to some places. Yeah, it's same. So this is DSW voltage and PCH always voltage. So both are same. Okay. So just one signal and it generates the PCH primary voltage. So after receiving the PCH primary voltage, then the PCH will receive PCH D power OK signal as an input, and with regard to this signal, it will send an output signal called SIO SLP sus signal to turn on the PCH primary voltage, that is 1.8 volt. So this will turn on 1.8 volt primary voltage for the PCH. So this is 3.3 volt primary voltage for the PCH, and this is 1.8 volt primary voltage for the PCH. And this will turn on only if the 3.3 volt D power OK signal, which is this one here, is active high. So with regard to this signal only, the PCH will release this signal as high, and this will go to this regulator here as an input from the PCH to turn on 1.8 volt primary. So we can copy this signal to confirm that. I think we have already checked this one here. So this signal goes to turn on the PCH primary voltage, and it's here. Yes, so you can see SLP sus signal is here on this side, and it straightly goes after this resistor to turn on the PCH primary enable signal, and this signal goes straightly to 1.8 volt always voltage regulator. Yes, it comes here at this point as enable signal, and this will generate 3 volt always as 1.8 volt always. So its current will be to the maximum of 2.3 amps. Typically you will find 1.6 amps here. Okay, right. Now when the PCH receives this 1.8 volt as primary voltage, it will generate using its internal regulators these two voltages here, one as PCH and one as FVT. And once the PCH has been generated these two voltages, then this regulator will generate a power good signal as an output signal to turn on this voltage here. So if you look at VCC in AUX voltage, so the voltage of this one also 1.8 volt, and you will find here also 1.8 volt. However, you will find 10 amps of current here, and you will find 1.6 amps of current at this point. And in order to turn on this voltage, you need to provide two enable signals here. One is this one, and the other one is from the PCH. So let me show you that. Okay, so this is the regulator that provides the VCC in AUX voltage for the PCH. So you can see its typical current will be around 10 amps. So the voltage will be approximately 1.8 volt. So the voltage is the same, but the current is different. So it's a high current, and the other regulator is a low current. So they are both used for different purpose. So if you look at this point here, the enable signal that comes from that regulator that produces 1.8 volt. So the power good signal from that regulator is fed into this regulator as an enable signal. And here we have VAD1 and VAD0. These are voltage identification signals. So this is sent from the PCH, and when the logics at this VAD1 and VAD0 is different, this regulator will generate a different voltage. So here we have those settings. So when the VAD1 and VAD0 is 0, you will get 0 voltage, and when VAD1 is 0 and 1, you get 1.1. When 1 and 0, you get 1.65, and when both of these VAD1 and VAD0 is 1, which is high logic, you will get 1.8 volt. So I think at this point you will get 1 at VAD1 and also logic high at VAD0, you will get 1.8 volt as an output here. So we have already confirmed that because we had 1.8 volt on both of those coils. Right, okay. So this is VCC in AUX voltage for the PCH. Right, so let me go to the power sequence. Okay. So after generating this voltage, this regulator also will provide a power good output signal confirming that the primary power good is also okay from this regulator. So now let me copy this signal to check wherever it goes. I think it should go to the EC chip. Let me see. Okay, primary power good signal. It is going to this OR gate here, and it is going as a reset in signal, and it is for the reset to the EC chip. You can find, yeah, it's here, the reset in signal that comes to the EC chip when the primary power good signal is being generated from the primary voltage 1.8 volt. Okay, so let me copy this signal. First we need to confirm which signal comes from the regulator there. Yes, okay, so this is the regulator that produces that 1.8 volt, and this is the power good signal from this regulator. Okay, yeah, it goes straightly to this point. After the 0 ohm resistor, this will be renamed as primary power good signal, and it goes straightly into the OR gate there. Let me copy this signal. Yeah, this OR gate here, and after this OR gate you'll get this signal as reset in signal, and this will be the reset to the EC chip. So in order to get the reset signal in this motherboard for the EC chip, we need to get either this signal or else this signal here, the primary power good signal. And basically this signal comes directly from the EC chip as an output here. So you can find it at this place, which is EC PCH power enabled. So it is an output signal. You can see the arrow pointing outward. So this is an output signal from the EC chip, and it will go straightly to the OR gate at this point here. So whenever you get high logic in any of this pin 1 or 2, you will get high logic on the output. So according to the OR gate logic, you should have at least one high logic as an input to get a high logic on the output. Okay, right. So you will get always high voltage or high logic at this point here. So that is fine. So once we receive this signal, the primary power good signal, then the PCH, wait a minute, I will show you that. Okay, so this is the primary power good signal. Here we have the EC reset, and this is the reset in signal to the EC chip, and once we receive this signal, it will send the RSM reset signal on the output from the EC chip as an input to the PCH, here. Okay, so if I go to the timeline sequence, yes, so primary power good, and then the EC chip will send RSM reset signal as an input to the PCH. Okay, then the PCH will provide ESPI reset signal. So what do you mean by ESPI? So ESPI is the latest or modern version of the LPC of the traditional LPC communication between the PCH and the EC chip. So in this motherboard, the MEC1515 EC chip uses ESPI communication between the PCH and itself there. Okay, so let me show you that as well. So let me copy this ESPI, and you can find, yes, 1.8 volt ESPI. Okay, yes, so you can see at this place, instead of LPC communication, this EC chip uses ESPI communication that communicates between the PCH and the EC chip. So this is the communication line only between the PCH and the EC chip. So once the EC chip sends the RSM reset signal to the PCH, then it will reset the ESPI interface between the PCH and the EC chip. So it will send the reset signal at this point as high so that the ESPI communication can be started. So when the ESPI reset is high, then the PCH will send sus clock signal to the EC chip. So this will be around 32.768 kilohertz frequency. This signal will be sent to the, or this frequency will be sent to the EC chip using one of its pin from the PCH. And this sus clock will be straightly from the RTC section of the PCH. Okay. So we can copy this signal as well to find it. Yes, so you can see sus clock signal that comes from the RTC section. So here we have the RTC crystals, PCH crystals here. So RTC reset. So from the RTC section, this sus clocks goes into the EC chip as an input. Okay. Yes, so you can check here at this point, MEC1515, and we have sus clock in signal. So it's an input signal. Okay. So after EC chip receives this sus clock signal, we will get another voltage called VCC-ST CPU voltage. So that is known as the sustained voltage for the CPU, and this voltage will be generated straightly from this voltage here. So this voltage will go into a switch, and that switch will generate as VCC-ST CPU voltage. So we can check that. So let me copy this signal here, the voltage. Yes. Okay, it's going to, yeah, this switch and input voltage, you can see it is 1.05 volt underscore out underscore FET voltage, and this will be switched to VCC-ST CPU voltage. So this is the enable signal for that. So we can find that. Wait a minute. Yes, so you can see, so this is the switch, and 1.05 volt is provided as an input, and we will get VCC-ST as CPU voltage, the sustained voltage for the CPU. The on signal is here, VCC-ST N underscore R. Okay, that's here at this point. Can connect it to this point here, and we have S3 signal and also co-VID signal. So this is from the VCC in AUX regulator. The same input signal from the PCA to the regulator is fed at this point here, and we should have either high logic on any one of the input to get high logic at this point. Then this regulator will switch this voltage at this point here. So let me check this one. So we can see that,
So if you look at these two signals here, so this comes from the PCH to turn on the 1.8 volt primary voltage or AUX voltage for the PCH. The same signal is fed into this OR gate here, and we should have at least high logic on any one of the input. Okay, then we will get high logic here. Either this should be low or this should be high, or both can be high, but both should not be low. If both of them are low, then we will get low on the output side. So either these two signals or the S3 signal should be there to turn on, either this signal or this signal should be there to turn on the VCC ST enable R signal here. Then this will go straightly into this switch, and it will switch 1.05 volt output fed as VCC ST voltage for the CPU. Okay, so there are two different gates, two OR gates are being used for this purpose to turn on this voltage as the CPU voltage. Okay, right. Okay, so after getting the VCC ST CPU voltage, now we can press the power button. So you can see before pressing the power button, we need to find all of these signals and voltages. So that should be before pressing the power button according to this timeline. So if you look at the debounce logic of the power sequence, the power button, and if you draw a line on this point here, and you can see all of these voltages are rising high before pressing the power button. So according to this timeline, these voltages, everything should be generated before pressing the power button. So let me see this signal here. So this is a PCH input signal and EC output signal. So this is the power button output signal from the EC chip to the PCH. So before that, we need to get the power button input signal directly from the power button to the EC chip. To find that, we can just copy this signal, and this will take to the EC chip. Okay. Yes, so here we have the signal. No, so it is JPWR, so which means it is a power button connector. So this is a power button input signal, so this is not an output signal. This is a power button input signal from the power button connector, and it is renamed here after the resistor. Okay, let me find it. Yes, so this one is not important, we can leave that. So you can see at this point here we have the power button or power switch in signal. So actually this should be the input signal from the power button connector into the EC chip. And here we have another power button signal from the SIO, I think. So this should be the output signal. So we can copy that and find it. Yes, so you can see here we have SLP SAS signal, RSM reset input signal, intruder signal. So this is the power management of the PCH. Okay, so the power button signal is an input, which is the SIO power button signal is an input to the PCH, and this is output from the EC chip. Okay, so this is correct, but this one is wrong. So this should be this way. It's an input signal. So let me go to the power sequence once again. So we need to rename this signal as EC input signal, and then we can't mention any signal at this point here. However, we can say SIO power button signal. This will be the output signal from the EC chip, and it can go to the PCH as an input. Okay, so this should be named at this place here. So this is an input signal from the power button directly to the EC chip. So that doesn't matter, no problem. So I want to tell you something. So according to this power sequence, so they are saying that they are mentioning these voltages should be generated before pressing the power button, right? Because they are all rising high before pressing the power button, okay? But actually some voltages within these points are being generated only after pressing the power button. Okay, so based on this we can make a conclusion that this power sequence is just a standard power sequence and this is not universal to the motherboard here, because some certain voltages in this motherboard can be programmed to be released or generated either before or after pressing the power button. So in this motherboard we have two BIOS, the PCH BIOS and also the EC BIOS. So we can program these BIOS to generate certain voltages either before or after pressing the power button. So as a good example, if you take the HP laptops like after 4th or 5th gen, those 3 volt and 5 volt inductor voltages will be generated only after pressing the power button. So, and if you look at the power sequence, they would have mentioned it as they are being produced before pressing the power button. So it doesn't mean that the power sequence are wrong. They are correct, but eventually when they are programming the EC chip, they have programmed the EC chip to release the S5 on signal, the S5 on signal or the EC on signal to be released immediately after pressing the power button. So what happens here when you press the power button, the first signal comes from the EC chip is the S5 on signal or the EC on signal. It will go straightly to the standby IC and the standby IC will produce 5 volt and 3 volt inductor voltages. Then these inductor voltages first will go inside the DSW, the deep sleep well of the PCH, and the PCH will be activated, and then only the SIO will send the power button output signal to the PCH to release the S4 and S3 signal, and then the board will turn on. So this is just to increase the battery efficiency and also to save power. This concept is being used here. The same concept is applied in this motherboard here. So certain voltages are not being produced before pressing the power button. Okay, so we can continue the power on sequence. So once we press the power button, the SIO will send the power button output signal to the PCH. Then the PCH will release all these signals here. So S5 signal, S4 signal, S3 signal, S0 signal, and finally this signal here, the gate hash signal, in an order. So once these signals are executed, then it will go to different sections to turn on the voltages. So here we have a voltage output, so it is a voltage regulator, and you can find for DDR4 RAM we need to provide VPP voltage, and that is the 2.5 volt, and this voltage is for the DDR4. So this S4 signal will go straightly to this regulator here to generate this 2.5 volt memory voltage, and this power good signal will go to the 1.2 volt DDR voltage regulator as an enable signal. Then this enable signal will generate this 1.2 volt output voltage. Then we will get a 1.2 volt VTT power good signal. Then after that, this S3 signal will turn on this voltage, which is the DDR termination voltage, which is half of the RAM voltage, which will be 0.6 volt. So we can copy this signal so that we can see which voltage is coming there to turn on, or which signal is coming there to turn on this 2.5 volt. Okay, right. Yes, so here we have the regulator that generates 2.5 volt. So once we get 5 volt always voltage and 3 volt always voltage as an input, and also we need to provide an enable signal here. So you can see SIO SLP S4 signal comes to this point straightly from the PCH and it turns on this regulator. So S4 signal turns on this regulator and we will get a power good output signal from this regulator. So we can copy this one and it should go straightly to the DDR 1.2 volt power for the DDR4 RAM here. Okay, it should go to that regulator. Yes, so you can see. So RT8207 has both the DDR voltage and also DDR termination voltage inside one regulator here. So once we get the 2.5 volt power good signal as 3.3 volt at this point on pin number 8, and this regulator will generate approximately 1.2 volt as an output. Then it will provide an output signal as a power good signal on pin number 10 as 1.2 volt VTT power good. And you can see at this point this enable signal at S3 here on pin number 7 is received to provide the DDR termination voltage approximately 0.6 volt. That is on pin number 20. Yes, here we will find 0.6 volt, and the enable signal for this one is here 0.6 DDR VTT on signal. So let me copy that to just to check wherever it goes. Okay, yes, it comes from this point. Yeah, so DDR VTT control signal should be there, then the output will be high. So when this when the A input is high, then Y input will be high, then this will go to the RAM regulator and will turn on the DDR termination voltage. Okay, now let me copy this one. Okay, it comes from, yeah, it comes straightly from the CPU, I guess. Yeah, DDR4 compartment. This is straightly from the CPU, not from the PCH, so it comes from the CPU. DDR VTT control signal. So in some motherboards you will find the 0.6 volt is being turned on by the S3 signal, but in this motherboard it is being turned on by the CPU itself. Okay, right. So when the DDR voltage is being given to the memory controller inside the CPU as 1.2 volt, then this signal will be released high by the CPU. So you can see high with 1.2 volt DDR. So when this voltage is there inside the memory controller of the CPU, this signal will be high and it will go inside this buffer and it will produce DDR VTT control signal to enable 0.6 volt as VTT. Okay, right. So 1.2 volt should be there to produce 0.6 volt, and that is turned on by the CPU in this motherboard here. Okay, right. So almost we have finished everything. Yes. So these all signals are okay. This one, yes, this one okay, this one is okay, and this one is okay. And here we have another one which is VCC-ST G CPU, which means sustained gated voltage for the CPU. So this is also another voltage. We have VCC-ST CPU. This one is just sustained CPU voltage, but this one is gated voltage for the CPU, which means it has a control signal by the CPU with the gate signal, which is this one here, and this will go straightly to this controller or the switch and it will turn on this voltage. So let me copy that. Okay, yes, so you can see it goes straightly to this switch IC and it receives the same voltage as this one. So VCC 1.05 volt output fed voltage, and it will be switched to VCC STG CPU, and the gate signal is this one here. The enable signal is this one here. So we can check that. Yes, so you can see here we have the controller, the switching IC. Once you get this signal as high at this point, you should get VCC STG CPU at this point. So I need to confirm whether this on signal is actually high or low. So we don't have any symbol at this point, so this should be active high. So we need to provide a high voltage like 3.3 volt at this point to turn on this voltage here. Okay, right. So this should be 3.3 volt in order to provide VCC STG CPU voltage. Okay, right. So let me go to the power sequence. Yes, so this is just a switching voltage of 5 volt and 3 volt from this point. Yes, so this always voltage will be switched to run power using this signal, S3 signal. So we can see that as well. Yes, so here we have 5 volt always to 5 volt run power and 3 volt always to 3 volts run power, and you can see the enable signal is S3 signal here directly from the PCH. Okay, and we will get all of these voltages. Okay, that is fine. And finally we will get this voltage as an input to the EC chip once we get all the power good from all of these regulators, and they will be collected together, and we will find the all system power good as an input to the PCH, which confirms that run powers are okay. All system power good is shorted to run power okay. Okay, right. So if S3 signal is active low, then we will find a low impedance at this point. So S3 signal should be high always to get all system power good as high. That's okay. So 1.2 volt VTT power good voltage will be renamed as all system power good after this resistor here. So this will be renamed again as run power OK signal, right? That is at this point, I think. So this one is not important here. Yes, so after this resistor you will find run power OK signal, and this should go straightly to the EC chip, I guess. I don't know, let me see. Okay, it is going to this AND gate here, so we need to find high impedance at this point and high logic at this point to get PCH power OK as high logic. So it is going inside this AND gate as well. Okay, yes, so it is going straightly into the EC chip MEC1515 to get the run power OK. And you can see this is on the 26 sequence at this point, and once we get the all system power good or run power OK, then it will turn on the IMBP VR enable signal, that is to turn on the or the CPU main power voltage. Okay, right. Run power OK signal should be high in order to turn on the IMBP VR on signal, the core voltage for the CPU. And VCC ST power good signal also should be there as a confirmation in order to generate this voltage. So let me confirm this as well. So actually the VCC ST power good signal is coming after the AND gate of this one here, S3 signal and VR on signal. After that we get the IMBP VR on signal, and after this level shifter we will get VCC ST power good signal. It means it confirms that all the voltages to sustain the CPU is already generated. So this VCC ST power good confirms that all of these voltages are present. Okay. So all system power good is okay, and IMBP VR on signal will be sent to this VR regulator to turn on the CPU voltage, and this will be generated based on this input signal here. So we can copy this signal. This is the main voltage for the CPU, VCC in voltage. Okay, so VCC in voltage. So here we have the regulator. Yes, it produces only the VCC in voltage. We get VR enable signal, VR ready is on this point here, and system data and system clock is on this point. So once the PL to reset is activated, and once the BIOS information is read, then the PCH will send the SVID command through the SDA and SCK line to turn the voltage of the processor dynamically. So the system data and system clock will be used by the CPU to communicate with the VR regulator here, the voltage regulator here, and it will adjust the voltage of the CPU dynamically according to the performance, right? So the current also will be varied and the voltage will also be varied, okay? And if you look at the supply voltage, the VCC in voltage, you have two phases, and these inductors are joined together and they will generate VCC in voltage, okay? Right, so the maximum current will be 47 amps and the typical current will be around 30 amps, okay? Right. So have you noticed on this motherboard here, they have mentioned only VCC in voltage. So let me tell you one thing here. So this is going straightly to the VCC core voltage for the CPU and also VCC GFX voltage or VCC integrated GPU voltage inside the CPU here. Because in older motherboards you will find separate coils for CPU core voltage and there will be a separate coil for CPU GFX, the graphics compartment. But at this motherboard, in this Tiger Lake 11 Gen CPU, you need to provide only one input voltage inside the CPU, and the CPU itself has the internal or integrated regulators that will switch this VCC in voltage to the core voltage, the core of the CPU, then as a system agent voltage, then also as the GPU, the graphics voltage. So I'll just confirm this with the datasheet of this CPU. Yes, so you can see F5VR, the CPU, this CPU has the F5VR, which means full integrated voltage regulator. Inside the CPU die, it has the internal regulator that will regulate the necessary voltage for the CPU cores, the cache, the system agent, and also for the graphics. So you need to provide only the VCC in voltage inside the CPU. So due to integration of the platform voltage regulators into the processor has one main voltage rail which is VCC in, and the PCH has one main voltage rail as VCC in AUX, and a voltage rail for DRAM, voltage rail for memory interface. Okay, the voltage rail VCC in will supply the integrated voltage regulators, which in turn will regulate all of these voltages here. So this VCC in voltage is going as an input to the internal or integrated voltage regulators inside the CPU die chip, and that die chip will generate all of these voltages. So one main volt inside the CPU in this motherboard here, unlike older platforms. So this is a unique one in this latest modern CPUs. So you don't have separate supply voltage for the CPU as graphics voltage or the core voltage. It will have only the VCC in voltage. Okay, right. So once these voltages are being produced, then we will get the CPU VR ready signal from the regulator, and this will go straightly to this point here, to the SIO, I think, the EC chip. Let me see. Yes, it is going to this AND gate here, okay. And run power okay, and VR ready signal should be there to get PCH power okay. Then the PCH power okay will be sent to, yes, to the PCH, okay, to the PCH. It will go straightly to the PCH. Yes. And you can see this PCH power okay is going to the internal AND gate, and you need to get CPU power good, system power okay, and PCH power okay to get the PLT reset as an output. With this one, you need to get the 24 or 25 megahertz clock frequency, or the oscillation should be there around 24 megahertz in this motherboard from the megahertz crystal, and then only you will get the PLT reset signal executed from the PCH, and then it will go straightly to the CPU. Then the CPU will officially start to work. Okay, right. So let me go to the power sequence once again for the last time. Yes, so PCH power OK is there. Then the CPU power good should be there. Then finally we will have the system power OK, and we will have the PCH PLC reset. So VR output will generate the PCH power OK. Then the CPU will output the CPU power good signal. So we will confirm that the CPU power good signal once again. Yes, processor power good signal. Actually it is from the, yes, so it is from the PCH actually. So once the PCH receives the PCH power OK signal, at this point it will send CPU power good signal. Okay, yes. Let me see it from the diagram here. So here we have PCH power OK, and we have the CPU power good signal. So they are receiving at the same time here, and system power OK also should be there from the EC chip. All of these three signals will be joined to produce PLC reset. And finally the EC chip will send the P system power OK signal, and all of these three signals will go to the AND gate. So we can draw it here itself. So you think this as an AND gate, you will get these signals as an input, and this one you will get an output as a PCH PLC reset signal, and you will find 3.3 volt at this point. So this is the total platform reset signal, and when this voltage is 3.3 volt, the total platform is out of the reset condition, and then the CPU will officially start to work. So I hope you got an understanding about the power sequence in the schematics here. So if you have any doubts, you can ask me, so I'll just try to respond. So if you got a good understanding of this power sequence, just let me know in the comment section, so I will be happy about it. Okay, so for the last time we can go to the power sequence based on the flow chart here. Okay, so this is the first voltage in this motherboard here, RTC VCC. So this voltage will be available at G3 state. So it will be always available in the G3 state. So during the G3 state, you will have only the CMOS battery in this motherboard, the adapter, and the battery, the system battery will be disconnected. So you will get this voltage, and it will go straightly to the EC chip as a V bat voltage, and also it will go straightly to the RTC section of the PCH. Then on the second sequence, you can find, now we need to connect the adapter here. So once you connect the adapter, you will get the raw voltage from the adapter, that is on the second sequence. Then the charger IC using the first and second MOSFET, it will produce this V plus voltage on the third sequence. Then the charger IC will detect the voltage on the adapter, and if it considers it as valid, then it will send a high logic on the ACOK pin here on the fourth sequence. So you will get 3.3 volt at this point if the adapter that is connected is validated. Also on the third sequence, once the V plus voltage is being generated, you will find this voltage here as 3 volt LDA voltage. So in this motherboard we have dedicated standby ICs for 3 volt and 5 volt. The 5 volt standby IC will generate 5 volt LDA voltage, and also the 3 volt standby IC will produce 3 volt LDA voltage. So this voltage will go straightly into the double diode of the RTC VCC, and you will get this voltage there. So when the ACOK pin is high logic on the charger IC, this pin is straightly connected to the EC chip at this point here. So when this is high logic, the always on signal on the fifth sequence, the EC chip will send it to both standby ICs here, 3 volt and 5 volt. Then the standby IC will produce 5 volt always and 3 volt always from the dedicated regulators. Then on the sixth sequence, at the same time, you will get the power OK signal. So this power OK signal will be fed into inputs of these two AND gates. You will have power OK signal one input here, and on the other AND gate you will get the power OK signal as an input. Then at the same time you can find here on the 6 sequence, you will get this signal from the EC chip here as VCC DSW enable voltage. So enabling the deep sleep well voltage, you will get this signal from the EC chip. After this 0 ohm resistor, it is renamed as this one here. So this signal will go straightly to this switch here that will switch 3 volt always into 3 volt PCH. So you need to get this voltage and this signal, you will get 3 volt always PCH. And also this voltage is straightly connected to this 0 ohm resistor, and after this resistor you will get this voltage here. So 3 volt always PCH and 3 volt DSW voltage is same, and you will get these voltage together at the same time once you receive this signal to this switch. Then on the 8th sequence, we can find that on this side here, you will get PCH D power OK signal from the EC chip to this AND gate here. So in this AND gate, we have two input signals. Power OK is already there. Once you get the PCH D power OK, then after this AND gate, you will get PCH D power OK signal, and it will go straightly to the PCH. You can see it will go straightly to the PCH. And with respect to this signal, the PCH will release SLP sus hash signal to high logic. So then this will go straightly to turn on the 1.8 volt primary voltage in this motherboard. So you can find it that on this point here on the 10th sequence. So this is on the 10th sequence, and that is here. Okay, so after the 0 ohm resistor, you will find this signal here, PCH primary enable signal, and it is straightly connected to this regulator here. So on the 10th sequence you will find this signal, then on the 11th sequence you will find this voltage, and on the 12th sequence this IC will generate a power good signal once this voltage is being generated. So this signal will straightly go to turn on this voltage here to this regulator as an input signal. So this power good signal is going to this regulator as an input or the enable signal. And in order to turn on this voltage here, we need to provide the VID signals from the PCH that is on the 13th sequence. So 12 and 13 should be there in order to get the 14th sequence. So if you look on this side here, we have the 13th sequence signals. So core VID, so these two are VID signals, voltage identification signals from the PCH. So once you get this identification signal to this regulator here and also the enable signal, then this regulator will produce this output voltage. Then on the 15th sequence, finally this regulator will provide a power good signal, and it will go straightly to an OR gate here as primary power good signal, and also you need to receive this EC reset signal. So it is an OR gate, so we need to just provide either one signal as high and the other can be low or high. At this time you will receive the reset in signal to the EC chip. So this EC reset signal is actually an output signal from the EC chip, but they have not mentioned it here, but we have seen it on the schematic. So it is just an output signal from the EC chip. Then the EC chip will send RSM reset to PCH. You can see that is on the 16th sequence. So in this AND gate you need to provide both signal as high in order to output high. Already we will have the power OK signal. Now if we get the RSM reset, then we will get PCH RSM reset underscore AND signal at this point here as an input to the PCH. Once the RSM reset is received by the PCH, then it will turn on the ESPI reset signal as high. And then on the 18th sequence you can find that is ESPI reset signal, and this will go straight to the EC chip to reset the ESPI interface between the EC chip and the PCH. So traditionally you will find the LPC communication between the PCH and the EC chip, and here you will find the ESPI communication, the advanced version of the LPC communication. This will be more smoother and fast communication between the PCH and the EC chip. Okay, Then on the 19th sequence we will find the communication between the EC chip and the PCH, and the EC chip will get all its information from the PCH through the SPI bus from the PCH directly from the ROM here, which is from the BIOS chip, and that is on 19th sequence. And if you look on the 11th sequence, after the 11th sequence 1.8 volt is being produced on the 11th sequence, and with 1.8 volt these voltage will be generated. So these are all internal voltages from the PCH. So once you get the 1.8 volt inside the PCH, the internal regulators will produce 1.05 volt and another 1.05 volt on 12th sequence. So that should be there on this point. Yes, so it's here after the 11th sequence. Once you get the 1.8 volt primary voltage, on the 12th sequence here you will get the power good signal. At the same time the PCH will produce these two voltages on the 12th sequence. So after the 19th sequence here, then on the 20th sequence we need to find it wherever it goes. Yes, on the 20th sequence the power button input signal will be there for the EC chip. Then with respect to the power button input signal, the EC chip will send the power button output signal to the PCH. Then the PCH will release all these signals here one by one in an order: S5, S4 and S3, right? On the 24th sequence you will find the S3 signal, okay? And on the 25th sequence we need to find it here somewhere. So you need to get this signal as well on the 15th sequence. So once you get the VID signals, then this SLP S3 signals, VCC ST override signals, either one of these signals for the OR gate should be high, then the output will be high. Then either one of these signals should be high to get the output on the VCC ST as high, because all of these are OR gates. Only one input should be high to get a high on the output. So on the 15th sequence you will get the VCC ST enabled, the sustained voltage for the CPU. This will be from this voltage here, and you will get 1.05 volt at this point as VCC ST CPU. That is on the 16th sequence. So now after the 24th sequence it goes straightly to this point here. This is also generated on the 24th sequence, and it will go to this IC, the switching IC, and it will produce another voltage that is on the 32nd sequence, okay? That is VCC ST, the gated sustained voltage for the CPU. That is on the 32nd sequence, okay? So we need to find the 25th sequence. Yes, so that is at this place here. So once you get these signals to turn on the run power 5 volt and 3 volt, on the 25th sequence you will get these voltages. And on 26th we need to find, yes, so the old system power good will be there at 26th sequence. So on the 25th sequence you will get the 1.2 volt VTT power good signal from the RAM regulator. So where is that RAM regulator? It's here, okay. It will receive the S4 signal to generate okay, so this is 2.5 volt VPP voltage regulator. It will generate this voltage and it will provide a power good signal, and this power good signal will go as an enable signal to 1.2 volt regulator IC here. Then that regulator IC will generate 1.2 volt and it will produce this power good signal. This power good signal will straightly go to a buffer circuit, and that buffer circuit will okay, after the buffer circuit it is connected together, and the S4 S3 signal and the 1.2 volt VTT power good signal will produce the old system power good for the PCH here, for the EC chip here, okay, right. And also here also we have on the 25th sequence we have the DDR VTT control signal. After the buffer you will get VTT control signal as an enable signal for the DDR termination voltage, which is 0.6 volt. Right, so after 27th sequence we will get yeah, on the 26th sequence you will get this one here, the IMBP VR enable signal. This is to turn on the main voltage for the CPU. So once all the system power good signals except the core are being generated, then only the EC chip will send the enable signal for the CPU core voltage. Afterwards, on the 28th sequence, we will get the enable signal for the core voltage, and it will go straightly to the core regulator of the CPU here. After getting this enable voltage, the Vout voltage of VCC in will be produced, and this regulator will generate the IMBP VR power good signal on the 30th sequence. And then this signal will go straightly into the so this will go straightly to this point here, to this AND gate as IMBP VR power good signal, and the run power good signal also going to this AND gate. After that we will get the PCH power OK signal. Sometimes there will be this ohms resistor there and the AND gate will not be used, so either one of this will be used and we will get the PCH power OK signal. On the 31st sequence we will get the PCH power OK signal. So PCH power OK signal includes the power good of the old system and also for the core voltage of the CPU. Okay. Then on the 32nd sequence we will get the CPU power good signal. At the same time, on the 32nd sequence we will get this VCC STG CPU voltage. And finally, on the 33rd sequence we will get the system power OK signal from the EC chip, and on the 34th sequence we will get the PLT reset signal. When the PCH PLT reset signal is received by the CPU, then the CPU will officially start to function. So here we have the SoC package. On this side here we have the CPU. On this side here we have the PCH. So PCH and CPU communicates between each other using the OPI interface, which is known as the on-package interconnect or on-package interface. First, the CPU will tell the PCH or request the PCH to read the BIOS information using the SPI interface from its BIOS chip. So all the information from the BIOS chip will be read by the PCH and it will send to the CPU. And first the CPU will initialize the RAM module. Then it will request the PCH to read the RAM information and it needs to send it through the OPI interface to the CPU. So first it will use the SM bus line to read all the information about the RAM, such as the RAM capacity, the RAM speed, and also the manufacturer of the RAM, and everything will be read using the SM bus interface and it will send to the CPU. And once the CPU receives this information, then finally it will send the DRAM reset signal to the RAM module to reset the RAM, and then the RAM will be initialized. Then all the information from the BIOS will be sent to the RAM module, and then the CPU will execute the BIOS from the RAM, and it will do a post test and we will get a display eventually. So this is how the power on sequence eventually happens until we get a display. Okay. So when you look at this power sequence, so this is based on the DC mode, which means the power sequence while having the adapter connected to the motherboard. So what if we disconnect the adapter and connect only the battery, or if we have only the battery power source, what will happen? So if you look at the charger IC here on the 4th sequence, this signal, the AC AV in signal, will go to low if the adapter is not connected. This will be reflected inside the EC chip on this pin here, and it will not release the always on signal on the 5th sequence because it is having a low logic at this point here. So 5 volt and 3 volt will not be turned on when only the battery power source is available on this motherboard here. So when the 5 volt and 3 volt will be turned on, so you need to press the power button here. So on the 20th sequence is there the power input signal, so you need to press the power button. Then Once you press the power button, immediately the EC chip will release the 5V always on signal. So this will turn on both the inductor voltages 3V and 5V. However, the 3V and 5V LDO voltages will be present on both the power source, either battery or from the adapter it will be present. Only the inductor voltages will not be present on this motherboard here if you have only the battery source. And also, this voltage will not be present on both the power source. Even though you have the battery power and adapter power, this voltage will not be present before pressing the power button. However, according to this power sequence, they are mentioning that this voltage will be generated on the 14th sequence. However, the power button input signal is on the 20th sequence. So some of the signals are being programmed using the BIOS in this motherboard here. So let me explain it to you how this voltage is being generated in this motherboard after pressing the power button. And when we saw the voltage on the inductor, the 1.8 volt inductor on this motherboard, we have two inductors. The small one got 1.8 volt once we connect the adapter, but on this coil here for the VCC in AUX coil, which has a high current for the PCH, the voltage on this coil appeared for a milliseconds and then it went off, and only after pressing the power button we will get this signal here. So what is actually happening? Why we are getting this signal, the voltage only for a second and it is going off, and once we press the power button we will get the 1.8 volt here. Okay, so now let's focus on that. So we can go to the 1.8 volt regulator for VCC in AUX. Yes, so this is the regulator that produces 1.8 volt with 10 amperes of current for the PCH, the auxiliary voltage for the PCH. So if you look at the enable signal for this regulator here, that is from the power good signal of 1.8 volt primary voltage regulator, and this will provide 1.8 volt as the enable voltage for this regulator here. And if you look at on pin number 17 and 18, you have the VID signals that comes directly from the PCH to this regulator here. And here we have the VID tables. So if you have 0 and 0, we will get 0. And these settings will be there. And if you have 1 and 1 on both the VID signal, you will get 1.8 volt. Also, if you look at the BIOS chip on this motherboard here, so we can see UC5. We have two BIOS chips on this motherboard, so both of them receives its power from 3.3 volt SPI. Yes, so serial peripheral interface. So we can search that voltage, and it is straightly connected to 3.3 volt always PCH. And this PCH voltage comes directly from the 3 volt inductor. So if we have only the battery source in this motherboard, then the BIOS chip will not be powered before pressing the power button, because before pressing the power button we will not get any of these voltages. So once you press the power button, 3.3 volt inductor will be activated, then we will get this 3.3 volt PCH, and the PCH will be activated or powered, then only the BIOS chip will be powered, then the PCH will communicate with the BIOS chip here. So before pressing the power button, PCH and also the BIOS chip will not receive any voltages. So if you look at this point here, so once you connect the adapter, now forget about the battery power source, once you connect the adapter, immediately we will get 1.8 volt primary power good signal, because this signal is turned on by SLP sus signal. So it will be generated once we plug in the adapter when the RTC section is okay inside the PCH, and we will get this voltage here. And this voltage is renamed as PCH power enable signal. Okay, power enable. And it will go straightly to the other 1.8 volt regulator, and once the regulator generated 1.8 volt, it will send a power good signal to this point here, and we will get the enable voltage. So that is fine. So once we plug in the adapter, we will get this voltage as well, 3.3 volt always inductor voltages. So at that time the BIOS will not be initialized by the PCH, because it will take some time. So before the BIOS is being initialized, this point and this point will be high because we have 3.3 volt at this point, and here also we have 3.3 volt from this regulator here as a power good signal. So both of these signals will be high, and the requirement for the VID signal also will be high for a few seconds, or like within a few milliseconds. So if it is high, both of them are high, we will get 1.8 volt. So immediately when we get 3.3 volt at this point and 3 volt at this point, we will immediately get 1.8 volt on the inductor here. But once the BIOS is being initialized and configured by the PCH, then it will stop or will send a low logic at this point here. It will then 0 volt and 0 volt at this point. Then we will get 0 volt output here. On the coil, we will get 0 volt on the output. So that's why once we plug in the adapter, we are getting 1.8 volt for a milliseconds until the BIOS is being configured. So once the BIOS is being configured, then the PCH will send a low logic at this point here on both of these VID signals. And the PCH will wait for the power button signal, and once the power button signal is received by the PCH, it will release both of these signals to high. Then this regulator will generate 1.8 volt. So this is the reason that we had 1.8 volt on the inductor for a few milliseconds. Okay, I think now you got a clear understanding on these voltages here. Okay, so now let's try to understand what is a CMOS in this motherboard here. So what happens when we reset the CMOS? So first of all, what is a CMOS? So CMOS means it is simply known as complementary metal oxide semiconductor, or in other words we can say it is a pair of MOSFETs. It is a pair of MOSFET. So we know inside the CMOS memory the BIOS settings are saved, such as the boot order, then whether the BIOS is a UEFI or legacy, and also the date and time of the laptop is saved inside this CMOS memory. So in order to save this information as bits inside the CMOS memory, the controller uses a pair of MOSFETs, such as P-channel MOSFET and N-channel MOSFET, in combination to represent either 1 or 0 inside this CMOS memory. So both of these MOSFET join together and produce either 1 or 0 as bits inside this CMOS memory. So that's why we call it as complementary metal oxide or complementary MOSFETs, which uses two MOSFET together to represent either 1 or 0 inside the CMOS memory as bits. Okay, so let's dive deep and understand what actually happens inside this CMOS RAM. So a complementary metal oxide semiconductor. So on the top we have P-channel MOSFET, and on the bottom we have N-channel MOSFET. So these combine together and produce CMOS. So the P-channel MOSFET is straightly connected to RTC/VCC or a pull-up voltage, and N-channel MOSFET is straightly connected to the ground point. And the gate of these two MOSFET is interconnected together, and the controller will drive this MOSFET. Will drive these MOSFETs. So if the controller wants to provide a 1 on the output side, or logic 1 or 0 on the output side, the controller will drive these two MOSFET, either P-channel or N-channel, to provide 1 or 0. And also the output of these two MOSFETs are also interconnected together, and we will find either logic 1 or 0. So if the controller wants to provide a logic 1 on the output side, the controller needs to drive the P-channel MOSFET, because P-channel MOSFET is the only MOSFET that is connected to a voltage line, and the N-channel MOSFET is connected to a ground point. So in order to drive the N-channel MOSFET, it needs to provide a high gate, and in order to drive the P-channel MOSFET, it needs to provide a low gate. So the controller will provide a lower gate to turn on the P-channel MOSFET to provide logic 1 on the output side. So if the P-channel MOSFET receives a lower gate, then it will connect the RTC VCC on the output side, and we will find logic 1 on the output side. And also, if the controller wants to drive the N-channel MOSFET, it will provide a high gate, and then the N-channel MOSFET will conduct the ground point to the output side, and we will find logic 0. So this is how the controller saves bits inside the CMOS memory using these P-channel MOSFET and N-channel MOSFET in combination. So that's why we call it as complementary metal oxide semiconductor. And controller does not always drive these two MOSFET. When the board is turned off, the controller also goes off. So at that time, if the controller doesn't drive the P-channel and N-channel MOSFET, then the data in it will be lost. So in order to retain the data, or in order to latch the data, it uses another pair of these two MOSFET. So let me show you that. So here we have RTC VCC connected to P-channel MOSFET, and also ground is also connected to P-channel MOSFET. And here we have the gates. The controller drives it. And on this side, the output line. And we have another same type of circuit which has P-channel MOSFET and also N-channel MOSFET. And the output is connected to this point here, and here also we have the gate interconnected together, and this input is connected from this output here. Okay, right, and this output is straightly connected to this input here, so it acts as a loop. For example, if the controller drives logic 1 on the output side here, so we will find 1 at this point here as an input. Okay, right. And this P-channel MOSFET will not turn on because it is a high gate. The N-channel MOSFET will turn on. We will get a ground at this point here. That is a 0. So this output is straightly connected to the input of this circuit here. So here we will have ground or 0. Either ground or 0. So if we have 0, the P-channel MOSFET will conduct RTC-VC to the output side, and we will have 1 on this point here. And then if we have 1 on this point, the N-channel MOSFET will conduct ground, and we will have 0 on the output side. So even though the controller does not actively pulse this circuit here, this circuit on this side will latch the signal that is given by this controller here. So if we have only 1 or logic high on this side, this circuit will ensure that it has 1 on this point on the output of this circuit, even though the controller does not actively drives this MOSFET here. So these two pair of MOSFETs and also pair of circuits are used inside the CMOS memory in order to save the in order to turn on the bits as 1 or 0, and also to retain the bits or to latch the bits even though the controller does not actively drives these two bits. Okay, so when it comes to CMOS memory in older laptops, like the laptops released in the late 20th centuries, like in 1980s, you will find dedicated CMOS RAM chips that provides a space for CMOS memory, and also it provides the real-time clock, which is 32.768 kHz frequency for the entire system. For example, that IBM ThinkPad 700 C series laptop has a dedicated CMOS RAM chip that provides a space for the CMOS memory and also real-time clock for the entire system. So this is the model of this laptop here. So IBM ThinkPad 700 C series. So this is very old one. So this laptop uses the CMOS RAM chip, dedicated CMOS RAM chip, to save the time, date and clock, and also some other CMOS information, and the real-time clock for the entire laptop. And if you look on this point here, we have the motherboard for this laptop, and this chip here at the center, this Dallas chip, it provides the CMOS RAM and also the real-time clock for the entire system. And here you have the data sheet. Yes, so this is the data sheet. You can see Dallas Semiconductor DS1287 real-time clock, and here you have different address buses. From this you can get all the information that is saved inside the CMOS RAM chip, and also this chip provides the real-time clock for the entire system. However, if you look at this model here, Motorola Semiconductors MC146818A, so this is the very popular CMOS RAM chip. So you have real-time clock plus the RAM inbuilt inside this chip here. So this chip was very famous during that period. This chip was used in most of the laptops, and now also they have used the same kind of this chip integrated into the PCH and also the SoC of the modern laptops in these days. So this is a very successful model, and the brand from Motorola which provides the CMOS RAM chip and also the real-time clock for the entire system. Okay, so we are going to refer to a data sheet here. So this is 6 series Intel chipset. So we are going to understand what is a CMOS from this data sheet, and also what is a real-time clock and what happens when we reset the RTC reset to ground, and what happens when this reset is activated. So we are going to refer with this one in this schematics here. Okay, now let me search for CMOS in this data sheet here. So this will take us to all the instances wherever the CMOS is mentioned. So the first place you can see, which is real-time clock. Yes, so inside the real-time clock we have 3 different sections. So the first one is the CMOS RAM. So the CMOS RAM is a part of real-time clock, and the CMOS RAM capacity is 256 byte in this chipset, and we need to provide a battery as a power source to retain all the datas in this CMOS RAM. So here we call it as RAM because it is a random access, so we can access any datas inside this 256 byte at any locations at any time. So that's why we call it as RAM. The second one is the integrated oscillator components. So inside the real-time clock we have 32.768 kHz frequency. So this real-time clock will generate this frequency using the 32.768 kHz crystal, and we will get this much of frequency from the real-time clock to the entire system. And also we have lower power DC to DC converter implementation, and inside this DC to DC converter we have 1.05 volt regulator. So the enable signal for this 1.05 volt regulated output is internal VRM enable. So once we get this enable signal, we will get the internal 1.05 volt as a voltage inside the RTC section. So we have 3 things inside the RTC section: the CMOS RAM, and also the oscillator components, and we have a regulator that provides a DC to DC converted voltage of 1.05 volt. So let us move to the other sections. Yes, not important. Okay, not needed. Yes, so this is important. So you can see this is the RTC reset. So you can see you have hash symbol. So whenever you have hash symbol, which means the signal is active low. So the purpose of the RTC reset, so whenever the signal becomes asserted, this signal resets register bits in the RTC well. I'll explain you what are these register bits later. So here they have given a note. So unless CMOS is being cleared, okay, unless we clear the CMOS, and this should be done in the G3 power state. So the Intel recommends us to reset this RTC section or RTC reset to ground, this signal to ground only during the G3 state, which means you need to disconnect the adapter and battery, and then only you need to reset this RTC section. So unless the CMOS is being cleared, the RTC reset input must always be high when all other RTC power planes are on. So when all other power planes are on inside the RTC, we need to make RTC reset as high always. And also, in the case where the RTC battery is dead or missing on the platform, the RTC reset pin must rise before RSM reset. So always the RSM reset, the RTC reset should be high before the RSM reset. So that's why we can see that we have two dual diodes to provide RTC VCC power. One is from the coin cell battery and the other from the 3 volt LDO voltage. So when the coin cell battery loses its power, the 3 volt LDO will provide a power for the RTC VCC. So that's why two diode implementation is used for the RTC section to provide the RTC VCC power either by the coin or from the 3 volt LDO voltage. And the next signal is the SRTC reset. So this signal will reset the manageability register bits inside the RTC well when the signal is grounded. Okay, and the same note is applied here as well. So that's it about the RTC reset. So we need to consider what are these register bits later, and then you will understand what happens when we reset the RTC reset to ground. Okay, right. So let us move on. Yes, so this is the VCC RTC, which is the input power for the RTC section of the PCH, which is 3.3 volt, can drop to 2.0 volt to a minimum state in the G3 state. So once we disconnect the adapter and battery, the RTC VCC voltage can reach up to 2.0 volt. So the coin cell battery can reduce up to 2.0 volt. So the threshold voltage is 2.0. Okay, right. And it is given as a supply for the RTC well. This power is not expected to be shut off unless the RTC battery is removed or completely drained. So this voltage should be always there. Okay, and here they have given a note that if you are going to remove the CMOS information inside the laptop, we should not provide a jumper directly from the RTC VCC to ground. We should not provide a jumper like this. However, we can use a jumper from the RTC reset to ground, and then the CMOS information will be raised. So we should not directly implement to reset the RTC VCC to ground. Okay, right. So let us move forward. Yes, now let's focus about clearing battery-backed RTC RAM. So clearing CMOS RAM in a PCH based platform can be done by using a jumper on the RTC reset. So we need to short the RTC reset to ground to clear the RTC RAM. Then the PCH will automatically delete all the information inside the RTC RAM. So the Intel recommends us to clear the RTC RAM only by shorting RTC reset to ground. And we should not, or we may not remove the CMOS battery and wait until the RTC details are being deleted inside the PCH. So we need to short just the RTC reset signal to ground. Then the PCH will understand it and it will automatically delete all the informations inside the RTC RAM. And also we should not short the VCC RTC to ground in order to delete the RTC RAM, because VCC RTC is the input supply for the RTC section, so we should not implement to short VCC RTC to ground to delete all the RTC memory. So how can we clear the CMOS information using the RTC reset? So a jumper on the RTC reset can be used to clear the CMOS values. So we need to short the RTC reset to ground, then the CMOS values will be cleared. So when we reset the RTC reset signal to ground, when we pull the signal to ground, two kind of things will happen. One is the CMOS values will be deleted, and also some of the configuration bits inside the RTC power well will be reset to default. So when we reset the RTC reset to ground, CMOS values will be deleted, and also some of the important configuration bits inside the RTC power well will be reset to default. So let me explain you what about the configuration bits later. Continuing the line, so when the RTC reset is tapped to ground, so when we short the RTC reset signal to ground, first the RTC power status bit will be set. So this bit will be set to 1 when we reset the RTC reset, when we pull the RTC reset to ground. Okay, so this signal here inside this range, the bit 2 is the RTC power status bit, and this bit will be set to 1, so its default state will be 0. And when we reset the RTC reset, or when we pull the RTC reset to ground, this bit will be set to 1. This bit will be set to 1. So when the system boots in the next time, the BIOS will detect that the RTC reset event has happened, as we have 1 or logic 1 on this range in the bit 2. So then it will automatically delete all the CMOS values. So once we reset, once we pull the RTC reset to ground, immediately all those configuration bits will be set to default. Set to default means everything will be 0. If it was 1, then it will be set to default as 0, all those bits inside the RTC power well. Okay, so first the RTC status bit will be set to 1, and those configuration bits in the RTC power well will be set to their default state. So default state means everything will be set to 0. BIOS can monitor the state of this bit. So this bit means the RTC power status bit. So the BIOS will monitor this bit when it boots in the next time, and manually clear the RTC CMOS array once the system is booted. Okay, so everything is clear. So when the RTC power status bit is set to 1, then the BIOS will monitor this bit when it boots in the next time, and it will manually clear the RTC CMOS array once the system is booted. The normal position would cause the RTC reset to be pulled up through a weak pull-up resistor. Yes, so we use a weak pull-up resistor, and usually you will find around 20 kilo ohm resistor for the RTC reset. That's why we call it as weak pull-up resistor. And in table 519 shows which bits are set to their default state when RTC reset is asserted. So when we pull the RTC reset to low, all of these bits in this table here will be reset to their default. So I will explain you this table later. So this RTC reset jumper techniques allows the jumper to be moved and then replaced, all while the system is powered off. So Intel recommends only to pull the RTC reset to low only in G3 state. So G3 state means no battery and also no adapter. So we need to reset, or we need to pull the RTC reset to low only during the G3 state, which means we need to have only the CMOS battery on the motherboard, and then we can reset the RTC reset signal to ground. So that's why while the system should be powered off, and then only we can reset the RTC reset to ground. Then once booted, the RTC power status can be detected in the set state. So first we need to reset the RTC signal to ground, and then once the system is booted, so once we get either battery or the adapter power, then automatically the system will be booted, and then we can find that this signal, this bit, RTC power status bit, will be in the set state, which is 1. Then automatically or manually the PCH will delete all the information inside the CMOS array. Okay, so moving down, we can find the table there. Yes, so figure 519 has all the configuration bits that will be reset when we pull the RTC reset to ground. So you can see all of these bits from this point down to here. So all of these bits will be set to their default, that is to 0, when the RTC reset is pulled to ground. And particularly this bit here, the RTC power status bit, only this will be set to 1. So when we reset or when we pull the RTC reset to ground, this bit will be set to 1, and then the BIOS will detect in the next boot and will erase all the CMOS information. So once we pull the RTC reset to ground, all of other bits here will be set to their default. So you can see these bits in specific locations here. So these are all different locations, and these are all in the same location here, and altogether we have 8 bits. 1, 2, 3, 4, 5, 6, and for these two signals we have 2 bits per each signal. So altogether we have 8 bits in this location here. Okay, and some other different locations here we have. This one is different, and only this bit will be set to 0, and most of these locations have 16 bit of address, 16 bit of those bits, and then some of the bits will be 8 bits. However, when we pull the RTC reset to ground, only the bits that is mentioned here will be set to their default. Okay, right. Okay, now let's talk about some of the important signal from this table here. So the first one is the RTC power status signal, then the after G3 enable signal, power button override, then RTC event enable, sleep type, then the RI underscore enable signal, then the new century bit signal, and also the intruder detect signal. So all of these signals are useful here so that we can try to understand and the purpose of those signals in the PCH here. Okay, so first we can try to search this signal, the RTC power status signal. So usually this signal will be activated when we pull the RTC reset to ground. So the PCH will understand that RTC reset has happened, and then it will reset all of the other configuration bits and also the CMOS information. So RTC power status bit. So this bit is set when the RTC reset indicates a weak or missing battery. So usually when the RTC reset is pulled to ground, it indicates that the CMOS battery is weak or missing. So the CMOS battery is weak or missing. But usually we can short the RTC reset to ground in order to reset the configuration bits and also the CMOS information inside the RTC, so that we can reset the signal to clear both of these things inside the PCH. And this bit is not cleared by any type of reset. So once the RTC power status bit is set to 1, then no reset can clear this status bit. Only the software can clear it. So only the BIOS can set this bit to 0 in order to make it inactive. So once the BIOS has detected there is a power status bit being activated, then it will boot the laptop and it will post, then it will set this status bit to 0. Okay, it will set this status bit to 0. So only the BIOS can reset this bit to 0, not any other reset signal. So once we pull the RTC reset to ground, or if the CMOS battery became weak or missing, automatically the RTC reset will be activated, and every time the configuration bits will be set to 0 to default, and also the CMOS information will be erased from the CMOS RAM. Okay, and the next signal is the after G3 enable signal. Okay, so let me copy this. So have you ever noticed that whenever you reset the CMOS information, once you plug in the adapter, the board will automatically turn on? So have you noticed that? So this is because of this signal here, which is the after G3 enable signal. So let me explain it to you how it happens. So once you connect the adapter, the laptop will automatically turn on, and this is the reason for that. Okay. So in the G3 state, we can see there is no system battery and also the mechanical switch, which is the adapter, also plugged out. So in the G3 state, we have only the CMOS battery. Only the CMOS battery is available in the G3 state. However, when the system power returns, so the power returns means either system battery or the adapter is plugged in, then the transition will depend on the state just prior to the entry to G3 and also the after enable bit. So if the after enable bit is set, then the transition from the G3 state to the next state will depend on this signal here. So the meaning of this line, the transition will depend on the state just prior to the G3 entry means, so when the laptop is working fine before the G3 entry in the S0 point, then when the system battery or the mechanical power is shut off or removed from the laptop, and once the power returns back, then automatically the motherboard will return to the S0 condition, because this is the state that was there before entering the G3 state. So the transition when the power returns will depend on the state before the G3 state, before the entry of the G3 state, when the laptop was turned on the last time. And also the after G3 enable signal is also really important in deciding what state to transition when the laptop power returns back after the G3 state. So if we move down, we can find this. So you can see, so once the RTC reset is pulled to low, this signal will be set to 0. So you can see if this bit is set to 0, the transition will be to S0. So this is the reason. So once you reset the RTC reset to ground, or once you pull the RTC reset to ground, and when you plug in the system battery or the adapter, the laptop or the motherboard will be automatically transitioned to S0 state. So without pressing the power button, the board will turn on. So when the after G3 enable bit is set to its default, so you can see 0 on each cases. So it will be 0. So here we have state at power failure. So it can be at any state during the power failure. It can be S0, S1 or S3 or S4 or S5. It can be any state, and once the power returns, it will be immediately transitioned to S0 state. So you can see it will be transitioned to S0 state. So even though your laptop is turned off before resetting the RTC reset, and once you get the power back, it will be automatically transitioned to S0. So this is the reason, even though we don't press the power button, the laptop will automatically transition to S0 state when we reset the RTC reset to ground, or when we clear the CMOS information. Immediately the board will transition to S0 once the power returns. So now we have an understanding about the RTC power status bit, then the after G3 enable bit. Now we need to find the power button override status signal. Okay, so we can find it here. Yes, so this is the power button override status signal. So this bit is set anytime a power button override occurs. So that is, the power button is pressed for 4 consecutive seconds. So if you press the power button for 4 consecutive seconds, then the power button override status bit will be set. So the power button override causes an unconditional transition to S5 state. So when we press the power button for a long time, more than 4 consecutive seconds, then it will transition to S5 state. At the same time, this bit will be set, and only the software needs to clear this bit, and once the laptop boots in the next time, then the BIOS will automatically clear this bit to 0 by writing 1 to this bit here. Inside the register it will write as 1, so the BIOS will acknowledge it and reset it to 0. So usually the power button override status bit comes only when we press the power button for more than 4 consecutive seconds. Okay, right. So now we have understood about power button override status, then the RTC event enable status bit. Okay, so the RTC event enable signal is like an enable signal to wake the system through the RTC alarm. So we can see we can set an alarm inside the RTC in the laptop so that it can be automatically turned on. So the laptop will automatically turn on even though we don't press the power button. So it can be activated through this signal here. So first the RTC event enable signal should be activated, then through the RTC status bit, then the board will turn on. So when this signal goes active as 1, then the RTC event or wake up event will be activated. And when we short the RTC reset, then this bit will be set to 0, then there won't be any wake up from the RTC alarm. Okay, and here we have the RTC status bit. So this bit will become 1 when the PCH receives a wake event through the RTC alarm. So we can wake up the system at a specific date at a specific time by setting the RTC alarm, and then the PCH will receive this signal and then it will wake the system from the deep S5 to S0. So once the PCH wake the system from the deep sleep through the RTC alarm, then this status bit will be activated, and then the software will clear this bit, the BIOS will clear this bit once it has been booted into Windows. On the next time it will remain as 0, and only when the RTC alarm is generated to wake the system from the sleep, then again it will be activated to 1. So if we go to the next section, we can find it clearly. So in this motherboard we have only 3 types of wake events. Okay, we have 3 types of wake events. So we can study this one, handling power failures. So depending on the power failure occurs and how the system is designed, different transition could occur due to power failure. So here we have the after enable bit. So we have studied this before. So this bit provides the ability to program whether or not the system should boot once power returns after a power loss event. If the policy is to not to boot, the system will remain in the S5 state, so it will not turn on. And there are only 3 possible events that will make the system after a power failure. So if the after G3 enable bit is not activated, then the system will remain at the S5 state. So usually when the after G3 enable bit is reset to 0, then automatically it will transition to S0 when the power returns. But if the after G3 enable bit is activated as 1, then it will not transition to S0 and it will remain in the S5 state. That's what we learned before. So there are only 3 possible wake events inside the PCH. So first one is the power button, the second one is the ring indicator, and also the other one is the RTC alarm. So when we press the power button status bit is set, and then the system will automatically transition from the S5 to S0. And here we have the ring indicator. So this is a wake event that is enabled by external devices such as from a PCI Express device, and also some computers can be turned on using the LAN cable. So that is mentioned here. So when the ring indicator goes low, then it is a wake event for the PCH from the external devices, and it will transition the system from S5 to S0. So RI does not have an internal pull-up, therefore if the signal is enabled as a wake event, it is important to keep the signal powered during the power loss event. So we don't have any internal pull-up for this signal here, so we need to always ensure that we have high pull-up for this signal when there is no any wake events enabled in this signal here, because when the power returns, if the signal goes active, So if the signal becomes active or becomes low, and when the power return, this status bit will be activated. The RI status bit will be activated, and the system will interpret that as a wake event. So we need to ensure that this signal is always high other than any wake events from this line here, from any external devices. Okay, and the next one is the RTC alarm. So we have studied this one. So RTC alarm is just a wake event through the RTC, the date and time. So these are the only three possible instances where the system can wake from the S5. Okay, so the next one is sleep type. So what do you mean by that? So let me copy this signal. Yes, so you can see this is the sleep type signal. So you have 2 bits. So different kinds of arrangement will be there for these 2 bits. So actually we have not 2 bits, we have 3 bits. So 10, 11 and 12. So we have 3 bits arrangement here. So when this bit is set to 0, 0, so when this RTC reset is pulled to ground, and this signal will be set to 0, 0, so it is completely an on signal. It becomes as on signal, typically maps to S0 state. So when the power returns, so this status bit will be set to 0 when the RTC reset is pulled to ground, then the system will automatically transition to S0 state. And after the laptop boots into Windows, then the software, which is the BIOS, will set these bits to somewhere here within this range, but not to this one. So only after the RTC reset is pulled to ground and the CMOS information are erased, only for the first time the system will be, the sleep type will be set to this range here, which is 300. And after the first boot, then the system, the sleep type will be set to somewhere at this point when the power returns, and only the power button signal will be there to wake the system from the S5. Okay, so if this signal, the sleep type signal, goes to 000, then once the power returns, immediately it will transition to S0. So this is similar to after G3 enable signal. Okay, right. Okay, now let's move to the next signal. So we can go to the page there, the table. So here we have the ring indicator. So we have studied this one. The next one is the new century status bit. So let me copy this signal so we can understand what is this signal for. Okay. Yes, so it comes to this point. So this is a century rollover signal. So whenever the century, that is, turns to 99 to 00, for example, if the year changes from 1999 to 2000, then the century bit will be set, the new century bit will be set, and it will create a system management interrupt inside the PCH, and it will set the new century bit when this century bit is activated. Okay, so that's it about the century bit here. Alright, so let me go to the table once again. And the last one is the intruder detect signal. So this signal will be activated when the chassis cover is removed from the system. So at that time, this signal will be activated and will notify the PCH that the cover has been removed. And that's it with the intruder detect signal. So all of these signals will be set to their default when the RTC reset is pulled to ground. Okay, so this what happens when we reset when we pull the RTC reset to ground. So there are two things. One, the CMOS values will be erased, and also all of these bits will be set to 0, which is to default state. Okay. Okay, so finally let's have an overall understanding of the RTC inside this PCH here. So this PCH contains Motorola MC146818B compatible real-time clock with 256 bytes of battery-backed RAM which is the CMOS RAM. So I have already explained you about this model, which is the Motorola MC model, which is this one here. So this chip was really famous in the 1980s. So this chip was introduced in the 1980s and this was really famous during those days. So this is a dedicated chip that provides the real-time clock plus the CMOS RAM. So the same model of this one is integrated into the PCH here, but this is the A model. However, the compatible B model is used inside the PCH here. The real-time clock performs two key functions. Okay, so first one is keeping track of the time of day. The second one is storing the data, so such as the CMOS information, such as the BIOS setting. So even when the system is powered down, all these settings will be saved. So this is done using the help of these two guys here. So 3-volt battery and 32.768 kHz crystal will support in keeping the track of the data and storing the system data as well. Okay, so the RTC also supports two lockable memory ranges by setting bits in the configuration space. So two 8-byte ranges can be locked to read and write access. So some of the admin passwords and also some of the security informations are saved inside this lockable memory range inside the RTC RAM. So RTC RAM also provide the security inside the RTC RAM. Okay. Additionally, RTC also supports a date alarm that allows for scheduling a wake-up event up to 30 days in advance rather than just 24 hours in advance. So for a maximum, you can set up to 30 days as an RTC alarm to wake up the system from the S5 state. So this will be helpful for server computers where you might set the RTC alarm to wake up the system to a maximum of 30 days in advance. So this is really a cool feature inside the RTC, so that without pressing the power button, your system can automatically turn on without any human effort. Okay. So I hope I gave you a clear explanation about the RTC and also what happens when we pull the RTC reset to ground and about the CMOS information, and then I have explained you about the power sequence in this motherboard here. So I think it is going to be a lengthy video. I hope it will be very useful for you guys. So take some time to watch this video, and if you have any doubts, just let me know, then I will try to explain it in my future videos. So thanks for watching guys. So stay tuned for our future updates, and bye for now.